Hello, everyone. We are a research team from Northeastern University. Today, we are excited to present our paper titled LE Object, Language Embedded Object-Level Neural Radiance Fields for Open Vocabulary Scene. This work introduces a novel approach to enhance robotic perception and scene understanding in open-world environments. The continuous advancement of zero-shot detection and segmentation technologies has significantly enhanced robots' ability to perceive and interact with complex environments. This allows robots to flexibly adapt to undefined environments without relying on predefined object or scene databases, demonstrating notable improvements in autonomy and adaptability. Next, we will introduce our method. The challenges in building an object-level mapping system are as follows. How can we continuously track objects and achieve high-fidelity object model representation in an open world? Additionally, to better guide robots in performing downstream tasks, we need to think about the question: how can we achieve a fine-grained understanding of the environment in an open world? Next, we will introduce our method. Let's talk about object segmentation. Our goal is to divide the scene into meaningful regions and accurately detect objects. To do this, we maintain a global list of all detected objects, each with a unique ID. Start with RGB images. Using the Yellow World method, we detect candidate objects in the current frame and get their bounding boxes. These boxes are then passed to the SAM segmentation model as prompts. Next, we iterate through all the bounding boxes of detected objects in the current frame, and the SAM segmentation model generates a segmentation mask for each object based on its bounding box. We combine two types of features: visual features from the clip model and spatial features from the 3D point clouds. These features help us associate objects across frames, ensuring that each object gets a consistent ID throughout the video. After associating objects, we merge the masks of candidate objects in the current frame to create the final instance segmentation mask. We crop the RGB images using these masks and feed them into the clip model. This gives us visual features that describe the objects in the current frame. Next, we obtain spatial features through the object's 3D point clouds. To move from 2D to 3D, we use depth information, camera parameters, and camera poses. This allows us to project the 2D segmentation results into 3D space, creating point clouds for each detected object. We clean up these point clouds using dbScan clustering to remove any noise. We obtain the object's point clouds, which are used as spatial features. In multi-frame observations, we continuously update the global list of objects and calculate similarity scores to match objects across frames. For each new frame, we detect M-candidate objects, each represented by its 3D point cloud and visual features. Then, we compare these candidates with the unknown objects from previous frames. The overall similarity between objects is based on two factors: spatial similarity and visual similarity. For each candidate object, we find the known object with the highest similarity score. If the score is above a certain threshold, we consider them a match. In this case, we merge the candidate object with the known object, updating its properties like the 3D point cloud and visual features. If no match is found, we treat the candidate as a new object and add it to our global list. After associating objects, we merge the masks of candidate objects in the current frame to create the final instance segmentation mask. This approach not only divides the scene into meaningful regions, but also accurately captures the boundaries of objects, even within complex structures. The result? A clear and consistent understanding of the objects in the scene. In this section, we discuss how neural networks can represent various scene attributes like texture, geometry, and semantics. Specifically, We use neural radiance fields (NRFF) to implicitly represent language attributes, training what we call a language radiance field. The features from the clip encoder align with the whole image rather than individual pixels, making it hard to use them directly for 3D language radiance field training. To solve this, we propose using object-level segmentation to align clip visual features to each pixel in the language radiance field. This approach resolves ambiguities in reconstructing language features at the point level. Object-level segmentation masks allow us to extract pixel-aligned clip features for each segmented region. Mathematically, the obtained object-level pixel-aligned language embedding provides accurate, contextual-aligned clip features for each rendered pixel from the 3D language radiance field. This alignment reduces ambiguity and enhances the accuracy and stability of language queries at the object. After obtaining the language embeddings, we align clip features between 2D pixels and 3D points to reconstruct the language radiance field. Since clip features are high-dimensional, directly learning them is computationally expensive. Inspired by LangSplat, we use a scene language autoencoder EC to compress these features, mapping them to a lower dimensional base. We then train a decoder DC to recover the original clip features from this compressed representation. Given the camera origin O and ray direction, we randomly select pixels in each input frame and sample along the ray direction. Drawing inspiration from Company SLAM, we use a hybrid encoding method combining one blob encoding and hash encoding. The geometric decoder DS outputs predicted SDF values and feature vectors, while decoders DC and DH output predicted C and H values. Next, we discuss the use of neural radiance fields to reconstruct the mesh of objects. Given a set of objects, each object has its own 3D point cloud, which helps us estimate the 3D boundaries. We apply object-level supervision only to pixels within the 2D bounding box of each object. For every object, we first initialize an object radiance field and use it to supervise the depth and color within the object mask. Each object is treated independently and has its own keyframe database. The specific training process for each object is as follows. Given the camera origin O and ray direction R, we sample along the ray direction within selected pixels. In the current keyframe, N pixels are randomly sampled within the object mask, and similarly, N pixels are sampled from the keyframe database. These samples are then combined. The sampling points are defined as ZOI. Each point has depth values and predicted colors. For each pixel, the rendered color and depth are CX and DX. Next, we will introduce our experiments. To evaluate the performance of our 3D open vocabulary segmentation method, we use the semantic labels provided by the dataset as query text and assess the results using MEOU and MAC. For evaluating open-world object reconstruction, we measure reconstruction quality using object accuracy, object completion, and object completion ratio. Based on the experimental results shown in Figure 1 and Table 1, we compared the performance of several 3D open vocabulary segmentation methods, including LSEG, LERF, 3DOVS, and LaObject. LaObject combines the strengths of object-level segmentation and clip encoding, significantly improving object recognition and segmentation detail handling. The MEOU and MAC metrics in Table 1 clearly demonstrate that LaObject delivers superior results in most scenes. Based on the experimental results in Figure 2 and Table 2, we compared the performance of our object reconstruction method. LaObject, as our baseline model, slightly outperforms VMAP in both object accuracy and object completion ratio, demonstrating strong reconstruction capabilities. It is important to note that the primary difference between LaObject and LaObject lies in the instant segmentation method used. LaObject employs the dataset's ground truth semantic classes for segmentation, while LaObject utilizes our developed open-world object instance detector. Although LaObject shows slightly lower edge accuracy compared to the ground truth-based LaObject, it exhibits greater adaptability in open-world scenarios. These results also underscore the close connection between object reconstruction accuracy and instant segmentation detector performance. In the ablation study, we examined the impact of segmentation, model selection, and feature choice for object association on the performance of 3D open vocabulary segmentation. The experiment compared the performance of SAM and mobile SAM under different feature configurations. Overall, mobile SAM's decoupled distillation approach made it more lightweight, with faster inference speed. The comparison of different object association features showed that omitting any features led to a significant drop in performance, regardless of whether SAM or mobile SAM was used. This indicates that both features are critical for object association and segmentation tasks. The best performance was achieved when both features were used, outperforming the use of either feature alone, demonstrating the effectiveness of combining visual and spatial features in improving segmentation accuracy. Thank you.